Good afternoon, everybody. Welcome to the next one in our series of celebrating faculty career colloquia. And just as a very brief reminder, this is something that we started more than a year ago, where we have senior faculty who have been in the rank of full professor for more than 7 years, are supposed to participate in this and present and talk about their experiences as a faculty member. And the intent is to ensure that they get a chance to share with faculty, students, staff what they've done, and also at the same time plan for the next phase of their career, and they meet with the dean and the department head. And today we're really privileged to have Professor Byron Pipes, who is going to be our speaker. And as you see, Professor Pipes is the John Gray Distinguished Professor of Engineering, and he is the only faculty member in the College of Engineering who has an appointment in 3 different schools: aeronautics, astronautics, materials engineering, and chemical engineering. And we were privileged to get him here to Purdue in 2004. And I'm really looking forward to what he's going to share with us. So please welcome, Professor.
Thank you. Thank you. Thank you. Good afternoon. It's always a challenge to try to speak to a group as diverse as you. And I've tried to put something in this talk for each of you. I hope I accomplish that as we go forth. I'm going to talk about a labor of love that has been my life in academia, because that's exactly what it was. Perhaps my family is the only love that exceeds this, and we'll talk more about that. Let's see, can we have some lights down? Who has light control? Maybe me. Maybe me. Does that help? Yeah, good. It gives you a little bit of ability to see the slides. I've made some nice slides, and I would like for you to see them as I'm talking, but at the same time I'd like to see you a bit more as well. Just a few words about the fact that what anyone does in academia is seldom done by themselves. I, perhaps more than average, love to work with other people. These names that you see on this list are a small cross-section of the group of people that I've worked with for the last 40 years. And it's interesting to me to try to put such a list together. So in many ways, it's a list that begins with the person that hired me into my first job, Jim Ashton, and it ends with my most recent students, suggesting that there's been a continuum of interacting with wonderful people for a long time, and the beauty of working with the group who are your graduate students is they never seem to age. So that puts us in a very interesting environment, a wonderful learning environment. I want to talk about a couple of things. I want to talk about some important questions we in the world of academia need to think about. Then I want to go back and go through a career, how it started perhaps, and then what phases it went through, and then talk about the body of work that goes with those phases. In each case, I'm going to stop and say, here are the lessons I learned in this process, and talk a little bit about the forces at work for the future, and looking to my own research future, what's it going to be like, or what's it intended to look like. So what are the important questions that we in academia live with today, especially if you're thinking about the future of the enterprise? These are pretty substantial issues. The sociology of work has changed a lot just in the time I've seen it. Knowledge capture and exploitation for prosperity. We didn't think about that too much. So long as we captured it and delivered it in the past, we didn't think too much about whether it created prosperity or not. But today, we're in that food chain. We're talking about it. We're talking about institutional and professional loyalties. Are we first responsible to Purdue, or are we responsible to our career field? The metrics of success. And if you don't believe that one has changed, just go on the internet and take a look. There are more measures today about how an academic scholar succeeds or doesn't succeed than could be imagined in years past. Furthermore, the whole, how does this thing work in an economy where we're systematically pricing ourselves out of reach from the common student, or the student that's prepared but cannot financially reach us? Add to that the fact that there's more to learn every day than there was in our time, and that doesn't seem to be abating in any fashion. So how will we accelerate the rate of discovery and at the same time sustain its results? How do we expand the learning process to lifelong learning? So what role will all this new media play as this develops? And what do we teach and learn in the future? It's not possible for me to teach all of the content that I both was taught and now have learned since then. These are really important questions, and I'm going to just let you relax for a moment and say I'm not going to take up any of them today. They're just too deep for us in some sense, but they are pervasive in our lives as we think about our enterprise. So I'm not going to do that. I'm going to talk about a single pathway through this very interesting set of conditions, the one that I know best, which happens to be my own. So where did all this start? And many of you who are sitting here today will be where I am in a few years. You'll be standing before a crowd. You'll be addressing, talking about your career. How do you know when it got started? In some cases, it's the choices that you made or the natural gifts that you possess that predispose you to some. But I think if all of us looked inward and tried to remember where this all started, we may or may not be able to come to it. I also want you to think about careers that we all are involved in as being journeys, not something that's written on a resume, but a path that we are all engaged in, and it's a journey. Along that way, there's deserts and valleys to be gone through. So my career in this endeavor started when I was first leaving college for my graduate degree. And many of you graduate students will face this soon. And I was looking for a job. This was 1969. It was an abundant time. 10 offers I had for work. Now this was also an odd time in that some of the offers arrived as telegrams. The only thing on the telegram was a fee or a salary and the location and a start date, and that was it. That's how abundant the opportunities were, and in some sense, how challenging it was. So we had double-digit offers. I began at a company called General Dynamics. It's not the same company today, but it was where they built, at that time, the F-111 aircraft. I knew nothing about airplanes, by the way. And I want to talk then about specific phases of my own scholarship. I want to trace you through what I think are contributions that I made in research. And along the way, I'm going to tell you stories about it. But the only way I can do that is to step back and say, well, what was it you were trying to solve? What were you doing at the time? Why did you choose those problems? Or how did they choose you? And you can see here, it's interesting that it's almost always sort of 5-year cycles that one goes through in working on a given set of problems and developing some answers to those problems. That's certainly true for me. The first problem I solved turns out to be, some will say, the most important problem I ever solved. I wouldn't disagree with that. I was lucky enough to solve a problem in composites, and these actually are the original figures that were drawn in 1969, 1970 by an artist. You'll notice that, well, the one on the left we had drawn with a modern computer graphic, but these others you can see were actually drawn by an artist. We didn't have computer graphics, as you can imagine. This particular work was called the free edge effect. It was an understanding that was missing. No one really understood what happens to layered systems when they're bonded together. Out in the interior, we knew instinctively what happened, but no one understood this, and we put the underpinnings and understanding in something called the stacking sequence effect and the free edge effect, which gives singular stresses at the free edge. A bunch of papers were published, the first of which was my first important publication, published with Nick Pagano. Nick was at that time at the Air Force Materials Laboratory, and I think the fact that I published this with him is also an interesting story, which comes from into the lessons learned. So what did I learn from that first set of work? And the answer was, solve an important problem. That's you do that one. In some sense, the rest take care of themselves, but solve it your way is another message. Pagano and I were actually competitors trying to solve the same problem. He was at the Air Force Materials Lab, had his PhD, was well ahead of me in years and experience. And my company sent me to talk to him thinking that he would fund me. Now, imagine that. The fellow that competes with you is going to fund you. What's the probability of that? They didn't tell me that was an impossible request, but I went anyway. Nick said, you have to solve this using elasticity in a closed form solution. I tried that for 3.5 months, maybe 4. Impossible. Couldn't do it. So I solved it with finite difference methods. It turns out that the numerical method worked. He said it couldn't work. You'll have a singularity, the problem won't work. It did work. I showed it to him, sent it to him in the mail, he was impressed. He said, this looks right. We need to publish this, or you need to publish this. I said, why don't you be my co-author? And that leads me to the point, never be afraid to invest in and trust a research relationship. This was a man who hadn't actually done anything in that first paper, but he became my lifelong partner out of that relationship. The next one I would like you to believe is something that we all should do. Let the unanswered questions that you have haunt you. It's in the shower, it's in the grass mowing, it's in the dishwashing times that the creative process works. And it almost always goes back to that unanswered question that's haunting you. By the way, that's exactly where the solutions come from too. And I got an analytic solution for that problem some years later. Why? Because it haunted me until I could do it. The next problem I took on was fiber orientation and flow. This is actually an extension, I love to tell people it's an extension of Einstein's work, but most people don't know that Einstein actually studied the viscosity of spheres and liquids. This was one of his pieces of work. And the chemical engineering world knows all about this. It's called suspension rheology. When we were molding things with discontinuous fiber systems, we had to find a way to predict how and where those fibers would go and what orientation state they would take. And we worked together for this, on this for a number of years and published maybe the first work in this for long fiber concentrations with Marcel Crochet, who was at that time at the Catholic University of Louvain. he became my partner, and Rick Givler was our graduate student that worked with us. And what did I learn in that work? Well, formulating a problem is almost as creative as solving it. And sometimes it is the most important point. We all know that asking the right question is more than half the answer. Turning the first solution to a problem is really pretty satisfying, but actually in this case there were two of us competing for this. A fellow by the name of Tucker at the University of Illinois, a young professor who had studied with Nam Su, was also working on this and did get a solution himself. And I have to tell you, if you read Tucker's work, you will see that he worked on that same set of problems for the next 30 years and has made a marvelous contribution to the field. We invited him back here to Purdue to participate in the Composites Design and manufacturing hub that we're building because we think so much of his work. So celebrating the success of others who follow or compete with you, I think, is another lesson that I would like to share with you. The next problem we worked on was one called notch strength. It turns out when you pierce a material with a hole, it has an intrinsic strength because that hole disrupts the load-carrying capacity of the material. While I was at General Dynamics, a man by the name of Max Waddups actually discovered that if you do some tests, you find out if you make the holes larger and larger, the strength goes down and down, and it reaches some constant value after the hole gets large enough. But as the hole gets smaller and smaller, the material gets stronger and stronger. Well, that could not be explained by stress analysis. And so people developed a number of theories which were not, I'd say, self-consistent. And we put some self-consistency to that and also developed an analogy with the time-temperature superposition principle of linear viscoelasticity, where you could actually shift, in this case, toughness characteristics across the radius of the hole. So these are the papers that we published. Weatherhold and Gillespie are both grad students. Weatherhold is a full professor at Buffalo, and Gillespie is my heir apparent at the University of Delaware Research Center, which I'll talk about in a moment. Simple ideas can be powerful. The idea that my colleague had developed at General Dynamics was a powerful one, but it hadn't been fully interpreted. And the analogy to linear viscoelasticity helped us. We demonstrated that heterogeneous materials often possess this intrinsic flaw characteristic, which was the fundamental basis of this work. Next, we turn to interlaminar fracture. Now, you heard that I talked about laminates and free edges of laminates. Now, then it turned out that we had all of the stress analysis that you could imagine, but we had no ability to use that in determining a material strength characteristics. And so we took fracture mechanics, linear fracture mechanics, and interpreted it for these materials. We were not alone in this, for sure. In many ways, we were among a large group of people working on this subject, but we focused on the experimental side of this and interpreting the experiments. We published a number of papers. Gillespie, again, shows up. Carlson turns out to be the co-author of a book I would write later, in later years, and Smiley was also a grad student. So what did we learn in this? Understanding measurement of important phenomena is really an important thing to do. It's not enough to model them. You also need to measure them, because the modeling and the measurements go hand in hand. So you can take classical, in this case fracture mechanics, and adopt it, but keep it simple, because this could get very complex. And I often quote in my classes that simple tests require complex analyses, and simple analyses require complex tests. It's become known as Pipes' law. Anisotropic rheology was the next area we turned to. And this really comes out of the same work that we were looking at in fiber orientation and flow. And it's an area that the liquid crystal polymer people have worked in for quite some time. But in fact, very few people in the composites field had worked in this at all. And still, there have been very few. It is to say that the flow characteristics of a highly filled system are also anisotropic as the mechanical properties are. This also shows the strain rate effect, which would be typical of a non-Newtonian polymer in its deformation state. But more important than that, look at the ratio or the differences, if you will, between the extensional viscosity in that array, which is shown below, the transverse extensional viscosity, the shearing viscosities, and the viscosity of the polymer. So the viscosity of the polymer is in the range of 1, and the viscosity of the extensional viscosity of the highly filled system in the order of 1 million. These are hyper-anisotropic material systems. And we have been working on those and, in fact, re-entering that area fairly recently. Here are the publications that came out of that. And I point to Anne-Marie Sastry on the first publication, who turns out to have been an undergraduate who worked with me 4 years. This is her senior thesis. It is the first paper in that area that we wrote, and it suggests that with a senior research project, a whole new field can be opened up to a professor on the one hand, and many of you know Anne-Marie Sastry. She's a full professor or named professor at the University of Michigan Mechanical Engineering. Today owns her own company, SACT3, which is a battery technology company. So this was her first creative work, and was a wonderful time to interact with her. So what did we learn? Well, truthfully, effective properties of highly filled polymers are anisotropic. That's not a new revelation to many in this field, but it was to me. Dilute suspension rheology, which is the basis of most of the work in this field, cannot predict the behavior of highly concentrated systems. I remember full well when we were looking at the fiber orientation and flow, we were saying, well, just how much fiber is in there if it's a dilute suspension? The answer is the fibers can't touch one another. Well, that turns out to be 0.01% for the fibers we were looking at. That is to say, essentially none. However, if you look at the concentrated systems, it turns out the kinematics are themselves simple enough that one can extract this information. The other point I want to make here, I add this at the very end, exciting research can be completed by administrators. Most of this work was done between 1991 and 1993. I was the provost of the university in those years. Sheet forming and drape forming and forming of these systems was still in its infancy in those days. And somebody said to me, we really need to understand how the fiber orientation is going to change as you move a flat sheet of orthogonal, inextensible fibers over a curvilinear surface. I said, oh, this is just geometry. Anyone can do this. And indeed, we set aside and we did this work. I set it aside as if, it's kind of important to do, but not very important. The next step is much more important. How does the polymer move through the system? How does the solidification? We actually did powder deposition and consolidation in this work. Well, as usual, I was surprised. Here's the publications. This includes O'Brady, who was a grad student from Ireland, Van West, who come back to work with me from Boeing. And unbeknownst to me, Van West took this work, his doctoral dissertation, that fabric forming work was his, back to Boeing, and out of that came a computer code which is today FiberSim. It's owned by Siemens. It's a multi-million-dollar company that provides this software for composites manufacturers today. The basic work was done by this student. Conor O'Brady is an illustration of the guests from abroad can bring new problems to you. He brought thermoplastic sheet forming to me from the UK, and we worked on that for a number of years. One of the problems, or one of the formulations that we developed, had inextensible fibers and incompressible liquids in terms of the mathematical constraints. I would just say to you, when you have that many constraints, you should hand that problem to someone else. Nanocomposites came along as in 1999 when I moved to NASA Langley, and I'll talk more about this in a moment. Nanocomposites became an important subject. Carbon nanotubes was on everyone's list of things to do, to work with, and there were unheard of or numbers that were being used about how great this material was. We were going to build, remember, a wire or a cable all the way to the satellite, and we were going to be able to, on the ground, have a direct link to satellite. None of this business of using, you know, modern microwave or something. We're going to use good electric wires. We're going to go up there. Well, this material to be that strong or that long with its self-weight has to be super strong, and everybody talked about that. And here are just some examples of carbon nanotubes. And here's some publications which I've done in this field. And one of the interesting things to me is it takes 2 slides to carry at least the bulk of those, suggesting that I spent a lot of time working on carbon nanotubes and looking at properties that might have occurred. As a matter of fact, I spent a lot of time trying to explain the question, if these things are so great, why don't we just build airplanes out of carbon nanotube systems? And this is what NASA thought, and they drew these graphs. You know, you've seen these strength versus stiffness graphs, and they've got this point way up here, and here's real materials down here, and we can make airplanes that are 1/10 the weight, and so on. And so I said, well, if you could do that, you probably should start by making a fiber, because the carbon nanotube, you remember how big this is, it's quite small, 1,000 times smaller than any fiber we've made today, so maybe we should make a fiber. So we tried that, and lo and behold, it turns out it made exactly a carbon fiber, the same ones we had before. So some of the things that I learned from that is this is a fascinating area, but that many of my colleagues in this research were failing to practice what I called intellectual integrity. They were not telling the full truth, and there was a lot of money at risk if you could meet some of these odd goals. For example, when they were looking at a stiffness of a carbon nanotube, they took out the material that's in the middle of the carbon nanotube, and when they looked at density, I'm sorry, it was the other way. Anyway, they got density and stiffness. They used 2 different cross-sectional areas to compute the same property, meaning it looked like it was much stiffer and lighter than it really was. What we learned is that the dispersion of these phases in another phase, namely polymers, is the dominant issue. It's almost impossible to do. And I think for that reason, the mechanical performance did not live up to the promise. Indeed, there are some opportunities coming around multifunctionality, electrical conductivity, a number of the really interesting characteristics. Multi-scale modeling. This work has been sort of transitions me back to composites from nano. But this is work that Professor Arvind Raman and I did together with our students. And I want to point it out to you because I'm particularly surprised and pleased about it. If you look at the right-hand side, what you see is a load deformation curve in an atomic force microscope. And if you look at that curve, you say, how in the world could anything have ever created that load deflection curve? I mean, that thing, what in the world, what phenomenon could have happened? Well, his student and my student got together and built models, and lo and behold, we were able to predict exactly the load deflection curve for a carbon nanotube sitting on the end of an atomic force microscope and having all of the interaction with a surface. You can see these multiple stages where the material, the nanotube is attached to the surface, the van der Waals forces have to be overcome as it peeled off the surface. So we studied van der Waal peeling, a number of phenomena, large deflection buckling theory. It took a number of models to put this together, but in the end, it worked. Here's the publications in the multiscale over in the composites area. Jonathan Goodsell, you all know, who's now in the aero department, is my student in that period, and so on. So what did I learn? The answer is, with computing power of the growth since 1970, that's the mark I use. When did I start? Multi-scale analysis that we've been talking about all these years is now feasible. Homogenization and dehomogenization are approaches. Dr. Yu's recently joined us, Weibin Yu, and his work in homogenization theory for structures is perfect for this discussion because it goes well beyond micro level into macro, but also down to nano. The interesting thing is that dehomogenization is an essential characteristic, and I won't spend a lot of time explaining that, but it is true. The time domain in the molecular modeling remains a challenge for us, and there is much more for us to do to make this connection between atoms and aircraft. Now let me turn to career, because some of you have always wondered, how could a person be this interested in this science and still also be interested in a leadership career? And I've show you here a collage of pictures. On the very left is actually a sketch of me when I started working at the Delaware organization. To the right, you see Steve Tsai, Zvi Hashin, and Jim Whitney. These are giants in the field of composites that I had the great pleasure to get to know and work with. The bottom picture is a picture of me at Delaware when I was the provost and the president at Rensselaer. On the far right is the first all-composite car, which was built, the Pontiac Fiero, in 1980, I believe, or 78, in that time frame, at the University of Delaware. We had the car at our research symposium. And now you'll see in a moment why I think that's important for today. So just follow those years for a moment. What happened? I discovered composites, not that composites were discovered, but I discovered composites for myself in that period of time. I started almost immediately building a center of excellence at the University of Delaware. Actually, I started at Drexel working on that. And then I got a chance to lead a college of engineering, to serve as a provost, a president. And then in 1999, I came back to the bench. So I've been back to the bench 15 years. And it's, of course, almost exactly expands the amount of time that I was in the leadership position. I went to NASA Langley to retool. I took the Goodyear chair at the University of Akron following that, and here in 2004. I just want to say that the person's picture who should be with that group is C.T. Sun, because perhaps why was it I never considered coming to Purdue before? And the answer is very simple. Purdue had the best academic in the world already. His name was C.T. Sun. He was here. Why would they need anyone like me? And one day, C.T. passed me in a conference and asked me if I would be interested in coming to Purdue. It's the first time I'd ever thought about it, frankly, but it didn't take long. I think he asked me in the morning, he said, well, then send me your resume. Next, at lunch, he saw me again. He said, don't forget to send the resume. I said, check your email. Didn't take long, and I was here. And this has been a wonderful time for me, 10 years. So I have the Bray Chair, named for John Bray, who was the man who was a chemical engineer who created the School of Materials Engineering. Here, I've been the director of the Institute for Defense Innovation, and now the CDM Hub, Composites Design and Manufacturing Hub, and hopefully next I'm going to be the Indiana Center of Excellence Director for the Institute for Advanced Composites Manufacturing Innovation. But I wrote along the way, I wrote a few papers about what I thought were important issues that should be dealt with. Note, it's interesting, I didn't spend much time writing these kinds of papers, and in some sense I wish I had. Arnold Kerr, who was a civil engineer at the time, said, Byron, we've got to really put some more emphasis on design. So he and I wrote this paper on why we need hands-on engineering education. It's kind of an interesting story. The Interdisciplinary Research Centers concept. Notice this is 87, so it comes as the time after we've won the National Engineering Research Center. I'll come back to that in a moment. The one that I had the most fun with was Phil Cont'd, and I wrote this together when he was CEO at Boeing. So what would be the global university? What should it look like? And it was published by the National Academies, and we had a lot of fun with that. Neither Boeing nor the academic enterprise have taken our advice at this stage. In 1984, I was lucky enough to be one of the first 6 ERC directors, and there's a characteristic of this Engineering Research Center's concept that I really strongly believe in, and you see that it's continued to be followed today. On the lower left are all the companies that I had developed in 1989, and above that are the companies that my successor has active in the center. The center is 40 years old this year. Jack Gillespie, who is its director, has all those companies involved. He lives in that building, which was built while I was there at Delaware, although I never lived in it. At Rensselaer Polytechnic Institute, as a president of an institution that had maybe a larger focus on undergraduate education than most, not than Purdue, but than most, I wanted to show you something that I took a lot of pride in, which is to reinvigorate these historic buildings, and to do so by demonstrating that the classroom of the future was something that should be invested in. This classroom is round, and these windows are actually windows. They're backlit now, so you can see what's etched on them. And what's etched on them are really symbols of technological innovations that had occurred at Rensselaer and for which it was famous. The concept was looking through the past into the future. That classroom goes back to the 1990s, and of course we've learned much more now with what we're doing, but I think at the time it was state of the art. At the University of Akron, the second, I think it's the largest polymer program in the country. I spent 3 years there and helped build the Wright Center of Innovation in Polymer Photonics. And notice it was founded the year I left and came here. The Institute for Defense Innovation here at Purdue has now lived a life that caused us to look at how Purdue can support the Department of Defense more actively. To that end, we created these centers of excellence at the, I hope this is up to date, and I'm looking at Dan and wondering if it is, but anyway, it's not, is it, Dan? I'm sorry. Anyway, this is an old slide, but it gives you some sense. We stood up these centers of excellence, and some succeeded and some have transformed. The excitement of my life today is this, the Composites Design and Manufacturing Hub. When I came to Purdue and looked at the what was happening in NanoHub, I was extremely impressed with that, with the capability. You know, we've spent 10 years here at Purdue. We have an extraordinary NanoHub where you can go and something like 250,000 people from around the world come together on this hub and work in nanotechnology. I thought, well, why can't we do that with composites? We really do need something like that. And so we created this hub. DARPA started the initial effort, and now it has some industry sponsors as well, using an industrial consortium. But its primary purpose is in certification by analysis. Let's remove all this empirical testing, simulation best practices, and then education and evaluation of simulation tools for composites. This leads me to kind of where am I going from this point forth? And it's an interesting question when you've looked at a field for a while. It was 1984 when I said the primary barrier to composites is manufacturing. It isn't synthesis, it isn't design, it's manufacturing. And we sold the ERC to the National Science Foundation. In many ways, that's still the case today. So the state of composites manufacturing simulation is far behind that of design for performance. And that's what we intend to take on. This is all happening in the context of a major development in Europe. The i3 and the i8 all-electric cars are also all carbon fiber structures. That is to say, the structural frame. You can see here the frame being assembled in Germany for the BMW i3. The i8 is I think a $100,000 car, but the i3, which I drove, and they have here in West Lafayette, is an affordable car. But did you see this story maybe a few weeks ago? In Chicago, we actually printed with additive manufacturing composite car. We started the process at the beginning of the conference and drove the car off of the floor at the end of the conference. This is Local Motors work, but in fact, Oak Ridge National Labs is behind this, and they're our partner in the future in this national organization. If we win this proposal, this is what it would be. The Institute for Advanced Composites Manufacturing. It is an organization that is located along I-75, and it has the 3 states that have 70% of the automotive manufacturing in the country: Indiana, Ohio, and Michigan. But it adds Kentucky, Tennessee, and Colorado with its commitment to wind energy. This is a program competing for $70 million in DOE funding. To get that $70 million, we've actually found another $195 million of match, if you can imagine such a thing. So there's lots of promise in the future, and if we, Indiana, get this, win our piece of it, and the whole thing has to be won, we will have simulation, additive manufacturing, and recycling will be our themes. So the simulation fits us perfectly, and we will build something called the Composites Virtual Factory Hub, resting very much on the Composites Design and Manufacturing Hub. I think additive manufacturing is probably the most exciting thing I've seen in composites manufacturing in my lifetime, and I think this is the place I intend to work from this stage on. Now let me give you a few observations which sort of go back to the original questions. And these are meant to be something for everyone in many ways. I believe it's the body of the work of the scholar that's most important. So sit down and look at your work and say, what do I need to do to make this a full body? And do it. And find ways to do it. It's also an important question to decide which direction should that body of work go. So how do I figure out what that should be? And I would argue that vision comes from thinking about the forces at play in the field that you're working. Why do you need to know what you need to know? It's a pretty simple idea. Third, I think most of the creative ideas that I've had have come out of life and death decisions. Frankly, you're at the edge, Pipes. How you're going to do this? And I've got multiple stories of that scenario, and almost invariably the best things I did came out of those times. Students, I always tell, good luck is the intersection of preparation and opportunity. And then this is not my quote, this comes from a Greek some years ago for sure. But what I add to that is of the two, the preparation is the only one you control. So control it. Be prepared for that opportunity. In our higher education system, the American model which we occupy, we need to be creating knowledge and transferring it at the same place at the same time. This argument about whether we should have research or teaching is a non-argument. I mean, it can go on and will go on in discussion, but the real truth, and I think we all here agree, if you do only one of the two, you can't possibly fulfill the promise that you've made. However, doing them both simultaneously, that takes a lot of creative work. I also like to talk about leadership of universities. Faculty should lead universities. Co-leadership is what we're supposed to be. And it's been my experience going around the world to universities, the more the faculty are involved in the leadership of the university, the higher the quality of the university. And the reverse is also true. Absolutely true, in my opinion. Now, as to big universities and small ones, they all have bureaucracy. And frankly, it's no substitute for us taking responsibility for what we do and what the institution does. This is my most important point about academic leadership. I do believe that integrity and unselfish service are at the heart of it. I have to tell you that the three heads that I work with practice this. And finally, there should be no excuse in higher education and in a research university for terminating one's search for knowledge. If you're too busy to do that, you shouldn't be doing it. You should be back learning how to create knowledge again. The further you separate yourself from that, the less effective you are, in spite of what you might like to believe. These are leaving thoughts and observations that I simply have wanted to say to you collectively for a long time, never have had really the platform to say them. You gave me the platform, so I decided to say them. I know full well that much of what I've said is a bit foreign to all of you, to be fair. But hopefully there's something that I've said that each of you can take away from this and use to make your success in this institution and in this labor of love that we all practice. Thank you very much.
I'm sure Professor Pipes will answer some questions.
I will. More light, I will. There we go, good.
Well, I think this has been quite a tour of your life, and I think a very impressive one. I've learned some things about you that I did not know, in spite of the fact that we've been together here essentially about the same time. So there are many things actually. In fact, this slide perhaps is the most important one, I think, of all of the ones you presented, which in my own mind summarizes the key nuggets, life's principles, so to speak, as an academic who also was able to, as in your case, accomplish great things administratively as well. So there are, each of them, I think, can have a full discussion. If we are careful, it could take a whole night of discussion.
It could.
Actually. But let me just ask you one that is not quite so obvious to me, which would be the number 3. That the most creative accomplishments often come from life or death decisions. Could you elaborate on that?
Well, the best way to elaborate on that is tell stories, I think. And the one I tell often, I've told it a number of times, is when I first started teaching at the University of Delaware, my chair asked me to teach senior design. Now, I was an untenured professor at the time. Senior design is a career-ending assignment. All of us know that, and therefore young faculty never get it, or should never get it, let's put it that way. But this particular head or chairman didn't seem to notice that or know it. They assigned it to me. Now, at the same time, I'm trying to build this career, build this research center, build this thing I had vision for. I thought, let's see, how do I do this? This is life or death, and it really was, truthfully. Well, I had heard somewhere in town that DuPont was interested in the fact that we were not doing a good job of senior design. So I visited DuPont, I visited Hercules, and I visited ICI. These were the three chemical companies in town. And I went in and said, you know, we know that you're concerned about the way we teach senior design. We'd like your help. I got their help. As a matter of fact, I don't think I delivered a single lecture in that class. I had experts. We had students, teams that were supervised by industrial advisors. This had never been done before. I was walking down the hall one day, and the senior professor in the department, whose vote I desperately needed for tenure, said to me, "Professor Pipes, the faculty and I are concerned about your design course." My heart went to my throat. "Sir," he said, "the students aren't going to any other classes." Meaning they loved my class. It was probably the best and most successful time it had been taught. Left to myself, I would have never done that. I would have never made those choices. I think there are times when you realize this challenge we have in front of us, all the things we're trying to do simultaneously, there are times when you have to make hard choices. And that really is the times when sometimes we are most creative. And by the way, that teaching scheme went on and was propagated. The next professor they hired actually assigned him to do it that way. But it had never been done that way. So I think the inventiveness that those kinds of tough decisions force you into, and I've got a whole bunch more as a dean and a president and so on, as you might imagine I would. But I think it sharpens you very clearly on what you must do and pushes you. It isn't that we don't make good decisions outside those conditions. We do, but I have to tell you, some of those creative things, and it led across a whole bunch of things with building the center and building departments and building schools and so on. I think I saw it over and over again, enough to say I've lived with it enough to believe it's real. So that's just one good example story that I tell from time to time. Other questions? Please, Jim.
Based on your experience, what has been the biggest challenge you faced in leading a large research team?
Money. I think large research teams, by their very nature, are expensive. They have to be funded. So unless you have a way to provide those resources, it doesn't matter that you know how to do it and you'd like everybody to do it, but if you have the resources to do it, then I think there are other problems. Don't get me wrong. I mean, but that's a necessary and sufficient one.
If you have money, what's the biggest challenge?
Oh, that's an interesting question. I think people who love to do that, they see everything as an opportunity, not a challenge. I think you're asking that in the context of how hard is it to work with independent faculty who have their own right to make their choices and don't really have to do what you say. You have no real authority over them. I think people always think about that as being the challenge we have in academia. I didn't find that particularly a hard problem. I found it, frankly, if you lead, namely you set the agenda, they help for sure, and they help you set the agenda, and then you make sure that the resources get allocated along performance lines, it falls right in line, just like it always does anywhere else. And I think the heads understand this. But Jim, that's my answer. Money is the first, and the second always was fairly easy for me. Please. Yeah.
Professor Pipes, kind of a follow-up question, but you seem to be very successful at forming teams. What's your strategy for putting together teams of people and researchers?
To be interested in what they're interested in, I think, is the most important piece of it. And the more you dig into what they do and appreciate it, the more willing they are to work with you. And I think that's true generally in all of life. I keep having to teach it to myself. Stand in front of the mirror and say, wait a minute, you're not so hot on this particular work, but do you know anything about it? Have you got any real knowledge? And the more you dig into what the people are doing around you, the more exciting it looks. So you got to reach beyond yourself. You got to reach into their area. You got to live where they live. You got to work with what they do, I think. And you got to, I guess you got to also practice the principle that it needs to be good for them, what they do. It can't just be good for you. But, you know, I know that sounds simple, but that's really a truth that I try to practice. Whether I successfully practice it all the time, that's another story, but I try. I think that's important. I mean, again, the three heads in this room, I have watched practice that. And look into the individuals that they have, you know, with their supervision. They try to think about what would be good for them and good for my school. And if you don't do it that way, it won't work, I think. I mean, it doesn't work. Short term, it does. Fear does amazing things for short periods of time, but that's not where we are, we academics. We are about our own work. Every one of us wants to work on the problem we're working on. It is the most important thing there is in the world, or we wouldn't be here, I think. Now, that's simplistic, I'm sorry to say. How about a student question? Some of my students are bound to have questions. Nick Smith always has a good question. I didn't mean to leave this last slide up, by the way. Certainly not the...
So, I guess I do have a question. You spent a lot of time in leadership positions. You mentioned here that life as an administrator need not terminate one's scholarship. How do you balance that? How do you spend adequate time being an effective leader while still continuing?
I think that answer is different for every person in the room who chooses to do this, or every individual. All I think the real right answer is make it a priority. If you make it a priority to work out physical exercise, you'll do it. If you make it a priority to keep active in scholarship, you'll do it. It isn't easy, for sure, but there are 100 ways to do it that if you'll just get out of the box a little bit and think about it, it can be done. Beg, borrow, and steal to do it. It doesn't matter. I mean, I'm serious about that. If you have to, you know, bribe somebody, do it, because it's essential that be part of your life. If you give that up, you'd be amazed how fast you separate yourself from everybody else. And if you don't, it binds you together. It's an essential ingredient. I really believe that. And I think we can make an argument that any organization is big enough to fill our entire lives. There's no question about that. And frankly, for 5 years, one did fill my entire life. I didn't do a bit of scholarship. Well, I had a postdoc, and we wrote some papers. But while I was president, I was 100%, you know, full life, just did that. Loved it, wonderful. But that is a 24/7 job. And I think you can. It's okay to for that period let go. Had I continued to do that for another 5 years, I wouldn't have been able to come back, I'm pretty sure. It's an interesting, I mean, even being away 5 years from a rapidly growing field is transforming. But so important to stay engaged in that which we value the most. I think they ought to teach too, to tell you the truth. That's harder to do because of the schedule, but research is not. Research is not on a time schedule like teaching. So I mean, of the two, if I had to choose one or the other, I would choose research because it keeps them intellectually engaged in our values in a way that nothing else does. So I won't add any more details to that. But thanks for asking that question, because these four individuals who are here with us today will tell you how hard this is to do. It isn't easy. If you want an easy life, don't be an administrator, because it is a life, in my opinion, of service to others. That means it's like having kids. You've just transformed part of your life to their support. That's also true for leadership, I think. And I mentioned vision just in passing. I think a leader needs vision about where we're going. And I think a leader is necessary for them to spend some time of their day, every day, thinking about where should we be going. I've got a lot of information here in front of me that others don't have about all the ins and outs of whatever it is I'm leading. How do I push that in a way that moves it where it should be, as opposed to where it will be if we do nothing? I really do believe in vision, to the point where I had a vision statement for Rensselaer, which is 25 words or less, that everyone could remember and use to make every decision with, that they made, from the registrar to the vice presidents. And I really believe in that concept as well. It drives you in a very nice way. Thank you for your attention. You've been very generous with your time. I do appreciate it.